Today we are going to do band theory and superconductivity for PhD entrance exams part 2. So let's get started right away. So we'll start with the first problem, and the first problem is like this. So what we have is we have an aluminum wire of diameter 0.9 millimeter carrying a current of 6 amperes. The density of the conduction electrons is 4.5 into 10 to the power 28 per meter cubed. And what we have to show is that the drift velocity is 1.3 into 10 to the power minus 3 meters. So it is not a difficult problem. So we know that current density J is equal to NeV. So N is the density, E is the electronic charge, and V is the drift velocity. So J can be written as I by area. So area here is given by the cross section area with diameter is 0.9 millimeter. So you just have to do the calculation. So I by A is equal to NeV. So from here you will get V. I think this is the wrong answer because I calculated by assuming I think this is the radius. So answer will be different. So you can find out what the answer is, drift velocity. So the next problem is an electric field of 100 volts per meter is applied to a sample of N-type semiconductor whose Hall coefficient is this. If mu n is the mobility is given, then this number is 0.33, then show that the current density J is given by so many amps per meter square. So we know the definition for Hall coefficient. RH is equal to 1 by NQ. NQ is the charge of the carrier. So from here you get N. RH is given, so you get N. So once you get N, so for current density you have to put N. Q is known, is the electronic charge. Mu n is given and E is given. So J you can find out J. So this is all straightforward. Now we go to the next problem. Next problem is about Fermi energy. So this is about semiconductors, intrinsic semiconductor. The Fermi energy of intrinsic semiconductor with upper edge of valence band denoted by EV and the lower edge of the conduction band denoted by EC is given by which of these options is correct? Okay, so let me tell you which option is correct. This is the option that is correct, and how do we know? So let us draw the picture. So this is my valence band. Upper edge of the valence band is given by EV. This is my conduction band is EC, and the Fermi energy Fermi energy lies somewhere here. Okay, the Fermi energy in this problem is given by epsilon F. So what happens is electrons from this near the band edge of the valence band get excited and go to the conduction band. So here we have conduction electrons and here we have holes. Right? We have holes. Right. And here you have electrons. So the conduction in this problem takes place both due to electrons and holes. Now we can calculate. This is all textbook stuff. So the the electron density in the conduction band is given by this expression. Okay, Fermi energy, lower edge of the conduction band, and this is temperature, etc., etc. Okay, and for the density of holes, this is the expression. Okay, so this is here this is the effective mass of the electron, this is the effective mass of the holes, and this is the upper edge of the valence band, this is the Fermi energy. And for intrinsic semiconductor, this is always true. So this is always true for intrinsic semiconductor, that intrinsic for intrinsic semiconductor, this is always true. Ne is equal to Np is equal to N. So if we equate these two, so so P, or rather it will be H here, so here it will be H, Ne is equal to Nh is equal to N. So if we do this, what we get is this. It's just straightforward, nothing much, so you get this answer. Okay, again using this, Ne is equal to Np, so we can multiply these two and then take the square root. Another way of writing this is this expression. This is this is written in terms of Eg. What is Eg? Eg is this is the energy difference between the lower edge of the conduction band and upper edge of the valence band. This is Eg. So this can be written in terms of Eg also, and this we are going to use in the next problem. For this problem, these two expressions are sufficient, this and this. This is for the next problem that we are going to do. So for the next problem, it is given that the conductivity of an intrinsic semiconductor is sigma 1 at T1 and sigma 2 at T2. Show that the band gap Eg is given by this expression. So you have been given the conductivities at two temperatures T1 and T2, and you have been given the conductivity at the two temperatures sigma 1 and sigma 2. So what you have to show is that the energy gap between the two bands Eg is given by this expression. So what is given is this one, sigma 1 is for temperature 1, temperature T1, and sigma 2 is for temperature T2. So this is the expression for conductivity. N1E is the charge carrier, is the charge of the carrier, mu holes plus mu electron, and this is the mobility of hole and mobility of electron. Here also this is N2, this is the carrier concentration at temperature 2, because both the electron carrier concentration and hole carrier concentration will be identical. So it is given by one value N2, here it is N1. And here mobility for holes is H and mobility for electrons is mu E. So if you divide, so what you get is, so you will get immediately sigma 1 by sigma 2 is equal to N1 by N2. So that is what we are going to do. So from here we can calculate N1. So from this expression, from this expression calculate N1. N1 is nothing but N at T1. N at T1. And what is it? Write it down, sorry. And N2 is n at T2 is this. Sorry. And that's it. So divide to these two expressions and you will get this answer. From here you will get this answer. Okay. So next we can go to a problem on superconductivity. So here it is given that the critical field of niobium is 10 to the power 5 amperes per meter at 8 degree Kelvin and 2 into 10 to the power 5 at 0 degree Kelvin. Show that the superconducting transition temperature is 8 root 2 Kelvin. So here you have to use this expression for critical field. So critical field is the field above which superconductivity is destroyed at a particular temperature. So at a particular temperature, when we have superconductivity, if the field exceeds that critical field, then the superconductivity is destroyed. So this is the expression, and you can see from here H0 is the critical field at H0 is a critical field at T is equal to 0. Okay, this is you can get, and HC is given. So H0 is given and HC is given at 8 degree Kelvin. So from here you have to find TC. So that is, once you know the expression, this is straightforward. What is TC? So next we go to the problem. Again, it's a problem on superconductivity, and here what we have is we are dealing with the problem on penetration depth. So the expression for penetration depth in a superconductor is given by, so penetration depth is the depth to which the magnetic field penetrates a superconductor, and it increases with temperature. So which of these options is correct? So actually this option is correct. Okay, this is an empirical formula, it's not something theoretically derived. This is the formula you get from experiment. So this is an empirical formula or empirical relation. This is an empirical relation, and we know that lambda increases with penetration depth, lambda increases with temperature. Lambda increases with temperature. So this is the answer. So we go to the next problem, and the next problem will use this expression. The London penetration depth for a superconducting sample at 5 degree Kelvin and 7 degree Kelvin is 41.2 nanometers and 180.3 nanometers. Show that the transition temperature is this. So this is simple, just you have to use this formula. So lambda at two temperatures are given, 5 and 7. So 5 and 7 are given. So from here, so here's the result from the previous problem. So you find out lambda at 5 degree Kelvin. Okay, so that is, you know from the expression. Lambda at 7 degree Kelvin, you know from the previous expression, and then here it's given. So you can do lambda 5 by lambda 7 and you will get the answer. Okay, so you have to do some calculations. You have to find out, I think you have to find out the transition temperature. So from here you can find out the transition temperature, Tc. Now go to the next problem. So this is a problem on extrinsic semiconductors. So in a particular donor, there are 10 to the power 13 in a particular, okay, so it in a particular, I think the problem is extrinsic semiconductor, yeah, extrinsic semiconductor, extrinsic semiconductor. So in an extrinsic semiconductor, there are 10 to the power 13 donors per centimeter cube with ionization energy ED of 1 milli-electron volt, effective mass of 0.01 times of electronic mass. So we have to estimate the concentration of the conduction electrons at 4 degree Kelvin. So thing is, there are 10 to the power 13 donors per centimeter cube, but not all the donors will contribute the electrons for conduction. Only some of the donors will be contributing electrons for conduction. So that we have to find out how many such donors actually contribute electrons for conduction at this degree, at this temperature. So for that so this is a picture. So here we have the valence band. Okay, so here we have the valence band, the upper edge of the valence band. Then you have the donor level. Actually this is given by E2 in the problem. Then you have the Fermi energy EF, and then we have this lower edge of the conduction band. So this is Eg. So Eg is actually much greater than kBt. Okay, much greater than kBt. If that this is, so there will be, so this transition from EV to conduction band is almost nil. This transition does not take place. So whatever transition is taking place is from the donor level to the conduction band. So the donor gets ionized in turn when it donates an electron to the conduction band. This is the ED is the energy difference between the lower edge of the conduction band and the donor level. So this is given, ED is given. So let's see. So we have to find out the concentration of conduction electrons, which is given by N. N is actually given by ND. So what is ND? ND actually is the concentration of donor electrons. ND is given here. This is ND. This is ND. Impurity concentration. So out of this ND, what do we have? N0. N0 will remain unionized. Will remain unionized. Unionized. It will remain unionized. And since it will remain unionized, the number of ionized donors will be ND minus N0, and that is exactly N. So if you calculate like this, first you calculate N0, then ND minus N0, you get N. You get this expression for concentration in the concentration of electrons, conduction electrons. Another way we can find out the concentration of electrons in the conduction band is by calculating n directly. So here you find out the electrons in the conduction band directly. So here you can see the expression for the lower edge of the conduction band. The energy for the lower edge of the conduction band is given. Okay, so there are two ways of finding it out. One indirectly using this, and one is directly. Both should give the same answer. Now at a very low temperature approximation, very low, it can be shown that this Fermi energy is almost equal to EC plus E2 divided by 2. That is, it lies somewhere in between. This Fermi energy lies somewhere in between. So you can use this result here, you can use the result here, and you can use the result here. And then using some approximation, you can directly come to this expression that we will use. So basically you have to multiply these two and then take the square root using the approximation. And so what we get is n is approximately equal to square root of nd n0, where n0 is, what is n0? N0 is this quantity. This quantity is n0. Okay, this is n0. nd is given. n0 you can find out. n0 is the quantity in the circle. Exponential minus ed divided by 2 kBt. What is ed? ed is this one. Sorry, it will be not g but c. ec minus e2. ec minus e2 is ed. And that is given. So in the problem, what is nd? Nd is 10 to the power 19 electrons per meter cubed. ed is 1 millielectron volt. Temperature is 4 degree Kelvin, and effective mass of the electron is, because we need effective mass of the electron to calculate n0, right? n0, because n0 is this, you have to know this effective mass, and that is equal to 0.01 times the mass of electron. So you can put all those things here, and what you will get, is this. So you can find out n is equal to this from this expression directly. So this is the concentration of the conduction electrons at 4 degree Kelvin. We go to the next problem, and two problems are there which are related to superconductivity. So before we go to these problems, the answer is very short, but some concept is involved. So I am going to just give you the concept in brief. So in superconductivity, there are two length scales. One is lambda, what is called the penetration depth, at the depth till which the magnetic field can penetrate the superconductor. And another important scale is the correlation length, which is given by psi. What is correlation length? Correlation length is the size of the Cooper pair. We know that superconductivity exists because two electrons become paired or two electrons become correlated. So what this psi gives is the distance. It gives the distance across which two electrons can get paired. Or form Cooper pairs. form Cooper pair. Okay, so these are the two, lambda and this. So in type 1 superconductor, this size of the Cooper pair is always greater than lambda. So what happens in type 1 superconductor? When you increase the magnetic field, the superconductivity is destroyed. There is no penetration of your your penetration of magnetic field. Superconductivity is straight away destroyed because of this. But in type 2, this is less than lambda. This is the opposite. In type 1 superconductor, the correlation length is greater than lambda. In type 2, correlation length is less than lambda. So in type 2, there are two critical fields. Hc1, which determines the penetration of field inside the superconductor, and Hc2, which determines the destruction of superconductivity. That is, the Cooper pair breaks down, and once the Cooper pair breaks down, there is destruction of superconductivity. So type 2 exists, actually type 2 superconductor exists in what is called a mixed state. What is a mixed state? So mixed state is the magnetic flux tubes pass through the superconductor. So let us have a look at the picture here. So this is a magnetic flux tube. So this is a cross-sectional view of the superconductor. So the magnetic field is going through this region, circular region. Okay, this is going through this circular region, and outside you have a superconductor. Just outside this tube, through which magnetic lines of force are entering this superconductor. This is the normal region, this is the flux tube, and outside we have a superconductor where there is no penetration of the magnetic flux. So this distance, this is the distance we are talking about. This is the typical penetration depth. This is of the order of lambda. Okay, and when this flux tube enters, when this magnetic lines of force enter through the superconductor, then you have supercurrents like this. Okay, you have supercurrents. Supercurrents are generated. So in this picture I have drawn only one flux tube, but there will be other flux tubes also. There will be many flux tubes like this. So there will be many flux tubes through which actually the magnetic lines of force will enter, and outside it will be perfectly superconducting. And when you have these supercurrents, we know that the flux is the flux which the supercurrents enclose is quantized. Okay, the flux is quantized. How? Now we will go to this problem. So the flux quantum is approximately 2 into 10 to the power minus 7 Gauss per centimeter square. Okay, Gauss per centimeter square. So this is the flux quantum flux or flux quantum. So a type 2 superconductor is placed in a magnetic field which is slightly increased till the field starts penetrating the superconductor. At this point, the field strength is 2 by pi into 10 to the power 5 Gauss. So here everything is in CGS system. So we have to show that the penetration depth is 100 angstrom. So now if you know the concept, the physics, this problem becomes simple. We know that a type 2 exists in a mixed state. So tubes of flux lines surrounded by superconducting current. So that means what is the flux? Hc1 into pi lambda square. So this is the flux. Pi lambda square is the cross sectional area of this tube, and Hc1 is the field that is entering this tube. So this should be equal to phi naught. What is phi naught? Phi naught is given. No, sorry, this here. Phi naught. It should be equal to phi naught. Phi naught is given here. That's it. Hc1 into phi lambda square. So from here you can find out what is lambda, because Hc1 is given here. This is Hc1. So Hc1 is given. Hc1 we know. Phi naught we know. So what we have? So find out lambda, the penetration depth. This is the concept. What is phi lambda? It's just one line. Next, a similar type of thing. So continuing from this is the next problem. Continuing from the previous problem, the applied magnetic field is further increased till the superconductivity is completely destroyed. The strength of the field is 8 by pi into 10 to the power 5 Gauss. Show that the correlation length is 50 angstrom. So when is superconductivity destroyed? Superconductivity is destroyed when what happens? The magnetic lines of force start interfering with the Cooper pairs. So psi is the distance across which two electrons can be correlated, that is the size of the Cooper pair. Okay, if the magnetic lines of force start entering into this region, then what happens? Superconductivity is destroyed. So the second field Hc2 times the cross section area, like this before, pi psi square, should be equal to the flux quantum. So because flux through any region surrounding a superconducting current is quantized, so this is the flux quantum. So Hc2 is known in this problem. Hc2 is known. Phi naught is known from the previous problem. Phi naught is known from the previous problem. So you can find out the correlation length from Hc2. Just like the concept is, so here Hc2 is always greater than Hc1. Hc2 is always greater than Hc1 here because your lambda is always greater than psi. Okay, so first comes penetration of the field and then destruction of superconductivity. Whereas for this is for type 2, so this is for type 2. Okay, so this is for type 2 superconductor. So this is the concept. Just like for lambda, this is the same concept. So as soon as the field lines start interfering with the Cooper pair, and it will start interfering with the Cooper pair when this condition is satisfied. Okay, then there will be destruction of superconductivity. So this is the problem and this is the solution. So we'll stop here today, and soon we'll come with the we'll meet with the third part. So thank you.